right. Today I would like to share a very interesting geometry problem with you guys. The configuration is actually quite straightforward. You have a triangle ABC. Okay, C is a moving point. Basically, shows all kind of possible configurations you have, and we also draw incircle inside. Basically, it's a circle that touches all the sides exactly at one point, or it's tangent to each side. And I mark the contact points as DEF. And I have two projections. So basically it means FG is perpendicular to AB and EH is perpendicular to AB, and G and H are their foot. So regardless how I move it, GD changes, DH changes, sine A changes, sine B changes. But what does not change is the ratio of GD over DH is equal to sine A over sine B. I mean, the ratio itself, of course, will change. You can see what happens. But their equivalence always hold, regardless of the position of C in the plane. So there are a couple ways to prove this quite interesting properties we have in the demonstration here. The way I do that is more like on the algebra side, and it uses a very classical formula. It's called a double angle formula in trigonometries, and plus this type of parameterization. So usually we call the side BC, opposite to vertex A, is A, right? But in this case, once we have the contact triangle, it's quite common to use something called semi-parameter coordinates to mark the length of the side like this. So we need GD, DH. So DG is AD minus AG, right? And AD equal to A, and AG is A times cosine A. So it is A times 1 minus cosine A. And DH is quite similar. It is dB minus HB. And dB is B. And HB is B times cosine B. All right. So the next step is we are going to find the ratio. A times 1 minus cosine A over B times 1 minus cosine B. Well, it seems we are kind of stuck here because we can do nothing with the cosine A and the cosine B just in the parentheses. However, if we use the double angle formula, so in this case, you can see cosine 2x is equal to cosine square minus sine squared, and this is exactly like 1 minus 2 times sine squared. So in this case, if we have 1 minus cosine 2x, so basically we can remove the 1 here, right? And it becomes 2 times sine square x. So cancel the 2's on the denominator and the numerator. We have GD over DH equal to A over B times sine half A squared over sine half B squared, right? So we are pretty close to the solution, but we just want to figure out what is A over B means. So if we go back to the original diagram, first recall that the incenter is the concurrence of 3 angle bisectors. So this angle equal to this angle, and this angle equal to this angle, right? And this circle is basically tangent to each side. So what if we draw a line that connecting the incenter and the contact point? It must perpendicular to the side, right? And let's call it R. So based on the very simple trigonometry, we can see that R over A is basically tangent half of angle A, equal to R over A, right? And tangent B over 2 is R over B. So you can see that if the A over B is basically tangent half B over tangent half A, which is sine B over 2 over sine A over 2 times cosine A over 2 over B over 2. So combine this relation and the relation here. So we have GD over DH equal to sine B over 2 over sine A over 2 times cosine A over 2 times cosine B over 2 and times sine half A sine half B, and the ratio squared. And if you look at this guy and this guy, we can perfectly cancel one term here, times sine A over 2 over sine B over 2. All right, then let's go back to the double angle formula. We can see that sine 2x is 2 times sine x cosine x. So what if we replace x here with half a? So on the denominator, we have sine half a times cosine half a. And if we times 2 on both denominator and the numerator, we have exactly the formula for double angle formula. Times 2 over 2. This and this. Sine A over sine B. Ta-da! And let's go back to the simulation. We have GD over DH equal to sine A over sine B. All right, that's it.